Okay, good afternoon, everyone. Before we get started, does anybody have any questions about quiz or anything coming up? So we do have a quiz this Friday. I can't guarantee it's going to be at the end of class. It'll probably be like towards the middle. It's going to be like 10, 15 minutes in duration. You're allowed to bring a scientific or graphing calculator, but not a phone or watch. You have to put those away during the quiz. And the formulas will be supplied on the sheet for the actual quiz. So you won't have to memorize anything. And then I also posted the second homework. But the first quiz that we're going to take this Friday will only be over something based off of the first homework. The second homework will not be considered fair game for the quiz. But a lot of the material from the second homework will be fair game for like the first midterm that we'll have. Okay, any more questions about that before I get started with today's lecture? Yes? It's only going to be like probably one equation. So probably not, but for the midterm, yes. As a study tool, I will give the midterm formula sheets early. Okay, more questions? Yes? Yes. Yes, the quiz will be based off of a homework question. It'll have numbers changed, but it won't be that different from a homework. It'll be pretty similar to one of the homework questions on first homework. Okay, more questions? All right, so we were talking about entropy last time, and we just started getting into it. So we'll talk about how energy is concentrated and how that's considered a less natural configuration than energy being spread out. And we did the example in class yesterday where one molecule starts out with all the kinetic energy, but through collisions over time, the energy is transferred, and then at a certain amount of time later, all the molecules have the same average kinetic energy. So this is the same idea. It's this energy spreading out as a spontaneous process that follows from energy conservation and conservation of momentum, things that are more fundamental. But what's interesting is that it does give us a irreversibility, a nature of irreversibility, where we have things proceeding in one direction but not the other. We talked about that with the example of the ice cube. It loses its shape, and even when it refreezes, it doesn't take that characteristic shape again. Or like dye diffusing through water, once that process occurs, it doesn't reverse. So there's this irreversibility, and we associate that with another property of the system called entropy. And so we're going to talk about entropy a lot more. And there's an analogy with temperature. So we can draw an analogy to this in temperature, since temperature is one way to measure the kinetic energy of the system. So cold, slow-moving particles will never give energy to a fast-moving system and make it even hotter when they are in contact. A cold system will always warm when placed in contact with a hot system until they both reach the same temperature. So we already kind of intuitively did this with our heat flow equations, because we had our rule about two things at different temperatures. When they put it into contact, they're going to reach thermal equilibrium. So now we can define the entropy as the spread or dispersal of energy. So when a system has very concentrated energy, it has low entropy. And in time, the system will have an increase in entropy, and the concentration will diminish until the energy is equally distributed across all the participants in the statistical system. So in other words, we have these gas particles, and both gases have the same thermal energy, but in one case, only one of the gas molecules is moving, and in the other, they're all moving. So which system do you think has lower entropy, A or B? Okay, so it's B, because this is the case where all the particles are dispersed. So the entropy is highest for B, because it's reached thermal equilibrium. So even though you might think of this entropy as disorder, that could be really confusing here, because a particle that's moving and the rest are not moving, that could feel like a more disorganized system, if depending upon how you think of it. So now we know that thinking of it in terms of order and disorder is not really accurate. The accurate way to think about it, at least in terms of physics, is in terms of energy and how the energy is dispersed. And if it's more dispersed across all the participants, then we have higher entropy. And systems typically start from a standpoint of lower entropy, and then the entropy increases with time. The entropy can stay constant as well, but overall in the universe, the entropy always increases through any process. But for isolated systems, the entropy can also decrease for a subsystem. And we'll talk about that more. We'll see the distinction there. Okay, but now we can say what the second law of thermodynamics is. So it's a statement about what the system can do spontaneously when left on its own. The entropy of an isolated system never decreases. It either increases until the system reaches equilibrium, or if the system began in equilibrium, it stays the same way. So in other words, if we're at a point where all the molecules are moving at the same relative velocity and they're all at the same temperature and the system's, there's no way for it to change, the entropy is just going to stay constant in a system like that. And it reaches a maximum when the system is in equilibrium. So equilibrium is an important point where the system achieves maximum entropy and then time evolution for the system halts. It basically reaches a stopping point. And we could take action and reduce the entropy of the system, but then the system is no longer isolated. So we could go and we could rearrange molecules and stuff, but then it's not an isolated system that was left on its own. So this rule applies to isolated systems specifically. And then there's some informal statements that are just kind of general points about entropy, which the first one is that when two systems at different temperatures interact, heat energy is transferred spontaneously from the hotter to the colder system, never from the colder to the hotter system. And then the second law, the other informal statement, is that the time direction in which the entropy of an isolated macroscopic system increases is the future. So we think of the arrow of time as proceeding forward and proceeding in this direction. It's kind of interesting too because there's sort of an analogy with this in cosmology, because as we're going to see, increasing the number of states available to the system is one way to increase the entropy. And what's kind of cool is that if you take a volume and you expand it, you actually increase the entropy of that system. So in a way, since the time of the Big Bang, we've sort of had an increase in entropy. And if you ask me what's like a general equation you could write down for the universe before the Big Bang, it could be a really simple one. It could just be like entropy was equal to 0 because you just had like no change, no increase in entropy. And then when the entropy gets started, you have an increase in volume, and then you have an increase in entropy for the overall universe. So that's just sort of an interesting way to think about that in the bigger picture. Okay, so since systems only evolve in ways that increase entropy, entropy defines this arrow of time. And we could think of the early universe as a system that had lower entropy than we see in the universe today, for example. And think of entropy as a measure of the spread of energy and how it's dispersed. So heating a system increases the thermal energy of the system and its ability of the system to disperse that energy, since it now has more energy to disperse. Thus, giving a system energy through heat increases the system's entropy. And cooling a system does the reverse and reduces the system's entropy. So if you cool down a system, you actually do reduce the entropy in that subsystem. But the point is that it always takes more work to do that in the first place, and that produces entropy elsewhere. So it's sort of like whack-a-mole. We reduce the entropy in one spot, but then more of it pops up someplace else. So that's how we see that entropy really always stays the same or increases when we look at the whole system. So the entropy of the system can change without heating or cooling as well. If we have gas molecules that are suddenly able to move in a larger volume, the entropy has increased without a change in thermal energy. A volume change is enough to increase the entropy. And this has important implications for, like I said before, the Big Bang and cosmology, where expansion of the universe was important. So we can see here that we can take this system of molecules and we can change its volume. And the thermal energy hasn't changed, but the entropy has. There's more entropy associated with this system because there's more places for the energy to go. So entropy is like a function of more than just temperature. It's also a function of position. And the more position possibilities we have here for these molecules to take, the more entropy we have. So these are some articles talking about information entropy and research being done in these areas. That's very interesting. Okay, so how entropy is related to work, how entropy affects the ability of a system to do useful work. An increase in entropy will cause a decrease in the ability for the system to do work. So this has applications to our ideal gas. So when we do things like we have a gas do work for us, we have a decrease in the ability for the system to do work. And this kind of really makes a lot of sense, because if we have some gas that we do some work and we say we compress a gas from, it was here and it goes down to here. So all the molecules are here and we have some dx and we did some work f dx on the system. And then we just let the gas do its thing and it expands and goes back to this position here. And then it stops at a certain point. Well, that increased the entropy because the volume expanded, the gas did work, and now it can't do any more work because it's done that expansion. So its ability to do useful work has diminished with its increase in entropy. And there was work done by the gas in the process too. So there's a connection between entropy and work as well. Okay, so here's a conceptual question. See if you can get this one right. Which of the following processes does not involve a change in entropy? We have an electric heater raising the temperature of a cup of water. A ball rolls up a ramp, decreasing in speed as it rolls higher. A basketball is dropped from 2 meters and bounces until it comes to a rest. And the sun shines on a black surface and warms it. So I want you to really think about this one. This question is definitely for those of you who remember physics from your last quarters. And really think about this one for just a second. And then we'll go over the answer a little bit. Which of the processes does not involve a change in entropy? Okay, so it's B. The ball rolls up the ramp, decreasing in speed as it rolls higher. Now, what's going on here? Why is it B? So here's why. Because it didn't say anything about there being friction involved. So all of the energy is conserved. But there isn't a change in energy. There's just energy's transformed from kinetic to potential energy. And the process is perfectly smooth with no friction along the way. So in that case, there's not a change in entropy. But for the basketball that's dropped, it bounces until it comes to rest. Well, what makes it come to rest? Friction with the ground. If there was no friction, it could just keep bouncing back to the same height every time. But it doesn't do that. Each time it bounces back up a little bit lower because that friction is taking some of that energy away and it's not conserved. So that frictional forces, non-conservative forces, are associated with entropy. And the rest of them we can see are pretty straightforward because we're heating the cup of water, so that's pretty simple. And the sun shining on a surface and warming it, well, yeah, that makes sense because that goes along with what we said before. So only in the case where kinetic energy is transformed into potential energy, there's no entropy change. So energy is transformed into thermal energy, and when that happens, we have an entropy increase. like friction. Okay, so if we have a phase change, such as melting or freezing, and it occurs at a fixed temperature, what happens to the entropy of water if a block of frozen water at 0 degrees Celsius becomes liquid water at 0 degrees Celsius? What do you think is going to happen? Are we going to have an increase in entropy for this system? What do you think? Yes or no? Hard to see, right? Well, think about it like this. When the water melts, is there more or less configurations for it to take? More, right? Because liquids, molecules can move around and they can take more orientations. Solids, they're kind of fixed in place. Ice freezes and forms like a lattice. And also, in order to cause a freezing, you have to take heat out of a system. And we remember from before, we talked about how entropy goes down for a system that loses its temperature. So the entropy is going to increase if it melts. So the entropy can change even at the same temperature if one of the phases of matter, solid or liquid in this case, is able to spread out the energy more. So ice is a solid, so the water molecules are frozen, and the molecules jiggle around it. And that's what the thermal energy is, but their energy is confined to small volumes around the lattice positions. But in contrast, the liquid water has more configurations, more positions it can take. And the number, as we'll see, entropy is related to the amount of configurations I can have of the same system. Redundant configurations, in fact. And what do I mean by redundant? I mean that, like, if we have the same energy, whether or not this molecule is here or this molecule is here, or we switch them, the more redundant states, degenerate states, where it's like the same energy but different molecules taking up different positions, but it still gives you the same net energy, the more entropy is associated with those states. And that's called the concept called multiplicity, which we're going to talk about more today. So in contrast, the molecules in the liquid water can move freely throughout the volume of the liquid, and this allows the thermal energy to be more spatially dispersed, just as it was for the free expansion of a gas. Thus, the entropy increases as the ice melts. So let's define what a microstate is. A microstate is a specific substate of a system that has many states. There's a microstate and a macrostate. And these are important concepts for like thermodynamics. So we have microstates, and then macrostate. We'll talk about which each of these means. So we can use the following model to understand the statistical definition of entropy in its relation to microstates. So let's say we have 4 coins, and each coin has 2 sides, head and tails. If we toss all 4, we have 16 possible outcomes, 2 to the power of 4. So we can use this formula for the number of microstates is equal to S to the power of P. So number of microstates is S to the power of P. And for our little system here, we had 2 possible states to the power of the participants, which is 4. So we have 16 total microstates. So we have states possible, and then to the power of number of participants, which is 4. There's 4 coins. And there's 2 states possible for each, head and tails. So we have 2 to the 4, 16 for 4 coins. So that's our basic formula. So 2 is for heads and tails, S is 2, P is 4. So we can define how many microstates we have given our degrees of freedom of the system. So how many degrees of freedom are there in this system? Just 2. It can be up, heads, or tails down. So 2 degrees of freedom, but there's 4 coins, so we have 16 possible states based off of that. Okay? So then we can model these states and we can tabulate all these possible results. We can have the state where it's tails, 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 or we can have the state where it's heads, heads, heads. Okay? And notice there's only one possible state for each of these where they're all tails or they're all heads. But look at this. There's other states where there's more possibilities. For example, there's states where there's 3 heads and 1 tails here, but this is also the case. There's 3 heads and 1 tails here. There's also 3 heads and 1 tails here, and same here. So what we can see is that our microstate is any one of these possible 16 states. Our macrostate is the property of having like all tails or all heads. It's this cumulative property that comes about. So that's how we get this concept of entropy relating to micro and macro states. Now I'm going to talk about this a lot more. This is just the start. Okay, so a macro state is a larger emergent property of a system that is less concerned with the details. In other words, for this case of the coins, why am I less concerned with the details? I don't care if the first one's heads or the second one's heads or which one. I just care if I have 3 heads and 1 tails. That's my macrostate property. See how I'm not concerned with the details? The microstate cares exactly which one has heads and which one has tails. And the most probable state is the one with the highest entropy. That's the one where we have collections of microstates that give us the same macrostate result. So you can see that's how the system is going to evolve to. If I have 4 coins, my macrostate of having 3 heads and 1 tail is much more probable than having just 4 heads. So on average, if I turn that number of coins into like millions of coins, I'm definitely, by the laws of probability, going to get a state that has an even mixture of equal heads and equal tails, because I have 50-50 probability for each. But if I do a really small number of coins, then that probability of getting it is going to drop. It's going to be more like 1 in 16, or it's not going to be less probable. It's going to be a little bit less probable when we have smaller numbers. But with massive numbers, the entropy drives it into like a very obvious concentration. So how does coins have anything to do with temperature? Here's how. If I have these molecules where the net kinetic energy of all the molecules in the system gives me my temperature, it's going to be even distributions of energy that's going to be the most probable. That's like having an even number of coin flips being heads and tails. Same kind of idea here. So while the microstate contains all the specific details of how the state is exactly composed, the macrostate in this example only cares about the number of heads or the number of tails, not the exact order in which they occur. Thus, for example, the number of heads and tails is a macrostate. In thermodynamic systems, pressure and temperature are also macrostates. So this is fascinating. It turns out that pressure and temperature are not like fundamental properties of each individual particle. They emerge upon lots and lots of particles interacting and sharing energy. So the energy, the temperature and pressure are examples of emergent quantities. And so is entropy. Entropy is also going to be an emergent thing. And just to go back to our thermodynamic system, the precise positions and momenta of all of our particles, those are the microstates. Whereas with our coin example, it was heads or tails. With the actual physics example, it's what's my position, x, y, z, and my momentum, px, py, pz. Those 6 variables, essentially, those collections for all the different particles, and their specific values, that's the microstate. So there's a huge number of these microstates available, infinite, like practically an infinite number, huge numbers of them. Okay, But let's stick with the coin example for a little bit longer. We can compute the likelihood of getting a macro state like 4 heads or 0 heads, and then compare the probability to other macro states like 3 heads or 2 heads. The multiplicity omega is the number of microstates that yield the macro state result. The multiplicity. So what's the multiplicity for heads is equal to 0, no heads? 1. What's the multiplicity for all heads? 1. There's only one microstate in both of these cases that gives me this result. But heads being 2 and thus tails being 2 has a multiplicity of 6. So that is the state with the highest entropy, and that's the most likely macro state that we're going to end up with based off of its multiplicity of microstates. How many macro states are there? Just one. The macro state is heads is equal to 2 and tails is equal to 2. One macro state here. How many microstates are there? 6. Why? Because there's 6 different arrangements, each one with different coins having different values, that gives us this result. So you can see how entropy is really based on probability and these fundamental laws of physics giving us this dispersal of energy that becomes favored when we have a huge number of interacting systems. So if you assume that each coin is fair with a 50% probability of giving a head or tails, getting heads or tails, then each of the 16 microstates is equally likely to occur. That is, the chances of seeing tails, tails, tails are exactly the same, 1 in 16, as seeing heads, tails, heads, tails. But the probabilities of the macrostates are not equal. There's only one way to achieve 0 macrostate. So its probability is 1 in 16, but there's 6 ways to have probability heads is equal to 2. So there's 6 of 16. So it's much more probable. But that's only for 4 coins. If we have more, the probability goes up much higher and spikes. So as the number of microstates increases to infinity, the probability of having n over 2, where n is the total number of heads that you have versus the coins, so it's half heads, half tails, it becomes 100% certainty when you have like trillions of these. It starts off kind of small for small systems and then spikes for large numbers. And that's the same thing as equal dispersal of energy across my molecules. Okay, so as n increases, we vastly increase the probability of finding the heads is equal to the number over 2, number of coins over 2 macrostate, because so many microstates yield this same result. That's the multiplicity. So the multiplicity becomes huge for this macrostate. So there's 4 important conclusions about microstates and their relation to macrostates that we can make. The first is that these random collisions and atomic level interactions, like coin flips, constantly change the microstate. So we have this system of particles, they're doing all of this stuff, they're not fixed in place. Just because the energy is zero, entropy I should say, just because the entropy is 0 doesn't mean that it doesn't have energy and it's not doing stuff. There's all sorts of activity going on inside this thing, but the macrostate, which is like the total energy that it has, doesn't change, because it's like flipping tons of coins and saying, is my distribution, am I going to be more likely to have more heads than tails after flipping billions of coins continually? No, it's always going to be about the same. There's about 50-50 of each. So that's how that comes about. The second thing is one macrostate is overwhelmingly more probable than the others, which means that its multiplicity, omega, which again is the number of microstates, is vastly larger than the multiplicities of other possible macrostates. So this idea is illustrated in that figure I showed you with the spike, because for large n, almost all the microstates correspond to the macrostates that are extremely close to this value and becomes this value at infinity, infinite number of coins. The most probable macrostate is the system's equilibrium state. So once an isolated system is in equilibrium, atomic level interactions will never cause it to change because the probability of being in any other macro state is essentially zero. So the atomic level interactions will occur. There'll be collisions, conservation of energy and momentum will apply, but those will do nothing to change the overall macro state, such as the pressure and the temperature and the total energy. Now, if an isolated system is not in equilibrium, atomic level interactions will instead cause it to evolve from the less probable macro state that it's in to the most probable macro state. So the example for that is atomic level collisions of a dye, causing it to diffuse across the water, and all the dye is evenly spread out after a certain amount of time. And so a non-equilibrium system, such as the dye dropped in water, will evolve toward equilibrium, not because it knows where equilibrium is or has any desire to be in equilibrium, but simply because equilibrium is overwhelmingly the most probable macro state to be in. And why is it the most probable macro state to be in? Because of the mathematics of the conservation laws. The conservation laws that will apply to all these tiny systems with a huge number of interacting pieces gives us this emergent entropy and this probable macro state from the multiplicity of the microstates. So we have omega, and it's related to entropy. Each microstate provides a different way to spread the energy. Equilibrium occurs from maximal dispersion, which is also the largest value of the multiplicity, omega. Thus, we can see that the multiplicity and entropy should be closely related. But how are they exactly related? Well, we can derive how. So we can take a volume and we can divide it into like 1,000 elements. So let's see here. I'll just take this, make a little volume here, and just imagine we make so many of these little boxes, 1,000 of them, okay? We divide it into 1,000 elements. Each of these can store one molecule. So we put a molecule in this box, and we put a molecule in this box, and we put a molecule in this box as well, and so on, 1,000 of them. But actually, only one molecule in total exists. So in one of these boxes somewhere there's a molecule. Sorry. So I misspoke there. Okay, so it could be here or it could be here. These should be a little smaller, but you get the idea. The volumes are equal. The molecule could be any one of these boxes. Okay. And so what's the microstate? The microstate is, it's in this box. No, it's in this box. So each one of those are separate microstates. And the macrostate is the property of just having one molecule somewhere. So each of the 1,000 locations is a microstate corresponding to one molecule, the one molecule macrostate. And if there are two molecules, the number of arrangements is now 1,000 to the second. If the bin size stays constant but the volume increases, then the multiplicity will go like this. So we have omega, the multiplicity, going like C times V to the power of n, where n is my number of molecules. And then V is my volume that can increase. Okay. So then try this conceptual example. If the volume of a gas doubles at a constant temperature, then what is the multiplicity increased by a factor of? So we've got this formula here, omega, C times V to the n, and now I say, what if the volume of the gas doubles? What is it increased by a factor of? Try to figure out, look at those results and see which one you think it is. Try to reason through it. Give everybody just like a minute here. Just be very like mathematical with it. Let it follow from the math and the rules of exponents and stuff. Okay? Okay, so the multiplicity increases from CV to the n to C times 2V to the n because the volume doubles. So now I have 2V to the power of n. So I doubled my volume, okay? But then this is both to the power of n. So I have to do 2 to the power of n, v to the power of n. So there's an increase there by a factor of 2 to the n, because before, this is what omega is now. Omega 2 is given by, it's the same constant, c, 2 to the n, v to the n, and the original omega, which is given by c, v to the n. So it's increased by this factor of 2 to the n. Does that make sense to everybody, how I got that? Anybody confused by that example? Okay, great. It's awesome. Okay, so now we can derive a relationship between entropy and this omega, this multiplicity. Based on the previous conceptual example, we can note that the multiplicity of a gas increases as it undergoes a slow isothermal expansion. So we've got this gas, and it's expanding from V initial to V final, and that's equal to VI plus dV. So let me sort of draw this out here, because I'm going to do a little derivation here, which is pretty cool to see. So we've got this, it's in a thermal bath that's surrounded by water, and it's a gas, and it expands. It used to be here, but it expanded up to here. And then it's got some heat flow through it, dQ, and it's got some temperature T, and its volume expands to V plus dV, where this dV is a differential volume expansion. We're going to use this to make a little differential equation here. So V final is equal to V initial plus dV, this little differential bit of volume increase. So this gas with initial volume VI is undergoing a slow, constant temperature, one temperature here, so it's isothermal expansion. And this process happens so slowly that it's essentially in internal equilibrium, and it's a quasi-static process. And there's an isothermal expansion that requires a heat input, so we'll let the environment supply an infinitesimal amount of heat dQ. So there is heat flowing into this to cause the infinitesimal volume expansion to V final is equal to V initial plus dV. So for now we're going to use the first law of thermodynamics, because we've got this change in internal energy is equal to work plus heat flow. So we've got a change in internal energy is equal to work plus heat flow, Q. Does everybody remember that from the first law? Now we can make this infinitesimal, so we can say, oh, there's just like a tiny little bit of this changing. So I can say D internal energy is dW plus dQ. It just means a tiny little bit, where dW and dQ are infinitesimal amounts of energy transferred to or from the system in mechanical and thermal interactions. And there's no change in the chemical energy. We don't have any bonds changing between this gas, and the thermal energy of a gas does not change in an isothermal process. So D internal equals 0. So we found then that the pressure volume work done on an ideal gas, dW, is equal to minus P dV. So thus, the isothermal expansion is characterized by this. So we have, we can move around dq a little bit over to the other side. So we can say that dq is equal to d internal energy minus dw, right? That's pretty straightforward. And then dw is equal to minus p dv. So dw equals minus p dv. So I can just put that there, plus p dv. Okay? But then dE internal is 0, so that goes away. So then we just have dq is equal to p dv, but then pressure is equal to nkt over v. Because remember, pv equals nkt, and we're using the Boltzmann's version of it. So this is like number of moles, I think. And this is Boltzmann's constant. Boltzmann's constant. I know we didn't use this much in the ideal gas, but it's the same ideal gas law. It's just we substitute, NR, big NR with little nk. Different, same fundamental value. Okay, and then we know what that is, right? Because we have that P is equal to nkt, same Boltzmann's constant, but I'm leaving out the subscript, over V. So then I can substitute that down here for this in this expression. So then I can just erase that, and then I have nkt over V times dV, and that's equal to dq. And then I can just integrate these. Okay? And then we know how to handle an integral like dv over v. That's just going to be like a natural log, ln of x, dx over, yeah. Does everybody remember that from their calculus? Yeah? Okay. Great. So then we have this expression. We're going to keep this, but we're actually going to keep this in the form where it's still differential volume. So actually, I'm just going to leave it like this. I'm not going to integrate it just yet. Let me erase that there. Okay, so that dropped out. That was 0. There is no dE internal for that. So it's just equal to this, nkt. And then we can bring this over to like the other side, and we have dq over nkbt. So nkt, dq over that is equal to dv over v. So we have dv over v. So now we still have our nice little differential equation here. Linear differential equation, because there's no powers of anything. It's basically just it's a natural log. But anyway, what does this represent? This is the fractional change in volume. So a fractional change in volume means I change this much with respect to my total volume. So this whole side is fractional change in volume. Right there. How much of my change I make from my total volume. Fractional change in volume during the isothermal heating is directly proportional to the heat, dq. Now, why is it directly proportional to the heat? Because this stuff on bottom is just a constant. It doesn't change. But this does change. When dq changes, dv changes. So these two changes are proportional in this differential equation. So now we can say that as the gas expands, its multiplicity, or the number of microstates, increases from some omega initial. So we're going to have a change in the microstates. Omega initial is equal to CVI to the n. And then we're going to have omega final is going to be CV final to the n. So here's the part where we relate our change in heat and volume to a change in microstates. So now we're looking at the microstates at two different times. And we need a relationship between the microstates at some final time to the microstates to some initial time, and that's going to be given by this. We take this constant and we factor out, because we know what V final to the n is. It's just V initial plus dV to the n. So we have omega final is equal to C, and then we have V initial plus dV all to the power of n. And then we don't know the constant of proportionality, but we don't need it to form a ratio. We can just do a ratio of the two omegas. So we're going to take a ratio of omega final over omega initial. And we know what omega initial is. It's going to be C VI to the n. And we know what omega final is. C VI plus dV to the n. And my c's cancel out. And then I have this expression here. Now what I can do is I can just divide this out by this, because I have a fraction here. They're both to the power of n, VI and that. So I can write this as VI plus dV over VI to the power of n. And then I can rewrite this fraction as being equal to, let's see, it's 1, because we have VI over VI, so we have, this is equal to 1 plus dV over V to the n. dV over V to the n. Sorry, that's a little bit messy. 1 plus dV over V to the n. Sorry, the chalk broke here. Okay, so that's going to be my ratio of these two is given by that. And I didn't change anything. It's the same content here. I did get rid of the subscript there because now I don't really need the subscript I, since everything is initial. We just have V. So the subscript drops out, and the volume's changing only infinitesimally, so there's no difference between VI and VF. So n is a huge number. It's a very large exponent. And one way to deal with it is to use a log. So we take the natural log of this expression, and then we have natural log of this ratio. So sorry, let me write this out on another piece of board. So we're going to go right down from the top and work our way down here. I promise this is one of the hardest pieces of math that you're going to have to see in this class. It's not all going to be this difficult. This is kind of like one of the harder derivations that we're going to do. So we're going to take the natural log of omega final over omega initial, and then that's going to be the natural log of this equals the natural log of 1 plus dV over V to the n. But when we take the natural log of something, the exponents come down out front. So we have n times natural log of what we had in parentheses. 1 plus dV over V. And that's the whole point of natural log. Natural log brings my exponents out front and makes it easier to manipulate things. Okay, so now we're starting to get something that's going to look like the quantitative relationship between the mathematical property of entropy and the microstates and the multiplicity. We're almost there. Okay, so dV over V is less than 1 because it's an infinitesimal expansion, and so we can just take this approximation of ln 1 plus a is approximately equal to a when a is much less than 1. So with that approximation, and we can use the first term in the Taylor series expansion, which You may have heard of this. It's a little bit more physics and mathy than some people might be used to. But basically, we can use this approximation, and it works out fine. So we have natural log of omega final minus natural log of omega initial, which is another way to write this fraction. Natural log of omega final minus natural log of omega initial equals this by the laws of logarithm, by the rules of logarithm. And then that's going to be equal to this n ln 1 plus dv over v. But now we have that little expansion where we got rid of the 1 from this rule up here. So we can just turn it into n over dv. So this becomes equal to, we get rid of this, and we just have n, and then it's going to be dv over v, because we take that Taylor series expansion and simplify that natural log. And that is again equal to dq over kt, which we had from up there. It links to this. Okay? So then we have our connection to micro and macro states, because we have a measurable macroscopic quantity, and we can calculate the change for the multiplicity. But I will go into more detail next time, since we're a little bit over time, and then we'll show how to apply this to problems. See everybody Wednesday.